Welcome to EF5 training. This is module 2.1 covering the topics of rainfall and potential evapotranspiration. My name is Race Clark. Today's training module is presented by the University of Oklahoma's Hydrometeorology and Remote Sensing Group. Thank you for joining us. So we're now into what we consider to be day 2 of EF5 training. If you haven't completed the first 4 modules that make up day 1, we recommend that you go back and do that first. And then once you've completed those, come back and join us here at module 2.1. But day 2 of the training is going to consist of this module about rainfall and PET. Then we'll move into discussing automatic calibration. And then finally, this training will wrap up with using and interpreting model output. So let's start by discussing a little bit about rainfall information in general. We need observations of the rain for a very important reason. The model can't produce runoff in response to that rain if it doesn't know what rain was falling to begin with. And so we call this rainfall information forcing. Rainfall is typically measured using rain gauges, which are point measurements, but we're using a distributed hydrologic model, that is a model that is producing gridded data at all points within the model domain. And so we need distributed rainfall information to go along with that provides rainfall information and rainfall estimates at each point within the domain. The way to do this is with satellites to the rescue. They can see clouds, cloud top temperatures, and in some cases, even cloud structures. There are 2 general ways for satellites to observe rainfall information. Those are passive and active. And so a good way to think about the differences between these 2 is to imagine that you're trying to look at an object in a room. If the room is well lit, like the room we're in right now, then you're acting as a passive instrument. You don't have to send information out into the world to get information back. The fact that it's lit up, that it's well lit by all of the lights, allows you to see everything you need to see. An active measurement, on the other hand, is like what a dark room would be like, where if you want to see the object, you need a flashlight or some other source of light or some other source of energy to be able to transmit out into the room and then wait for that energy to bounce back to you so you can process it and see the image. Satellites work in much the same way. A passive satellite instrument is only receiving information. And so this would be like infrared measurements from a geosynchronous orbiting satellite or a microwave measurement from a low Earth orbiting satellite. An example of this would be the TRIM microwave imager. Active satellites, on the other hand, those instruments are actually transmitting information and then receiving what comes back. And so examples of this would be like the precipitation radar on the TRIM satellite or the precipitation radar as part of the GPM mission. Passive measurements can occur over many different wavelengths, and these reveal different information in each spectrum. So, for example, the infrared spectrum is used to derive cloud top temperatures, and then there are relationships in the scientific research that relate those cloud top temperatures to rain rates occurring underneath the clouds. And so that's one way to get at an estimate of precipitation under a cloud. Another way to do this would be with multi-channel microwave measurements that can actually see through cloud layers. These are more complicated than the infrared relationships, but these exist between brightness temperatures and rain rates. And the way that the TRIM mission in particular works is it's actually calibrating microwave measurements to the precipitation radar measurements. So you have separate instruments that are all part of the same mission, and one of those instruments may be preferred over another. And so once you have the measurements or the estimates from one instrument, then you use those to calibrate the other instruments to make everything look nice and smooth and all put together. Now, geosynchronous satellites are one type of orbit that you can have with a satellite instrument. And there are good things about those, but there are also some negatives to them. One good thing is that a geosynchronous satellite is always looking at the same spot of the Earth's surface. In other words, it turns in tandem as the Earth below it turns. And so the pros of that are that it's always looking at the same area, so it has rapid updates. It can basically update as fast as a satellite instrument can work and transmit the data back to Earth. So you can get updates on the order of every 1 to 15 minutes. It also has really good resolution because, again, it's always looking at the same spot. And so you can get resolution on the order of 1 to 4 kilometers, 1 to 4 square kilometers per grid cell. It also gives you good coverage, nearly global, because, again, it's far enough away that it's looking at most of the Earth's surface at any one time. So if you had a constellation of these satellites, you could really see the whole Earth's surface all at once. There are some negatives, however. The type of instruments that these satellites use can't see through clouds. And if you can't see through clouds, you don't necessarily know that precipitation is actually occurring underneath them. Just because there's a cloud there doesn't mean that the rainfall is actually reaching the ground. And if the rainfall is not actually reaching the ground, it's not of very much interest to somebody who's running a hydrological model, because we care about precipitation that's actually reaching first the canopy layer and then eventually the ground layer itself. On the other hand, when it comes to low Earth orbit satellites, The pros and cons tend to be somewhat reversed. The pros here are now that we have multiple wavelength measurements, and those can often measure through clouds all the way to the ground, so you get a much better idea of what's actually happening at or underground, or at least under the clouds. They also have really good resolution. The cons, on the other hand, are that the update time or the revisit time is much, much longer. Low Earth orbit satellites are only sensing one small swath of the Earth's surface at any one time, and so you have to wait. If you're in a particular swath, once a satellite passes, you have to wait for it to come back to you again, and that process can take hours to even days. That also means, because you're only looking at swaths, that you have incomplete global coverage, and the swaths can oftentimes be very narrow. So, low Earth orbit satellites don't give you the full global picture in the same way that a geosynchronous orbiting satellite does. So, you might have thought that one way around this is just to combine the two or merge the two, and so that's actually what the TRIM mission does. They have a product called TMPA, which stands for Tropical Rainfall Measurement Mission, or TRIM, Multi-Satellite Precipitation Analysis. So this uses many passive microwave satellites with probability matching to the core TRIM satellite. So the core TRIM satellite has an instrument that's taking very good information about precipitation, and then you're using all of these other passive microwave satellites, and you're basically calibrating their results against that core instrument, and that gives you then the global picture you want. So the gaps in the low Earth orbit satellite coverage are filled with data in the gaps from the geosynchronous orbiting satellites. So this is what the TMPA product looks like at the bottom of this particular slide. It's available every 3 hours. It comes in on a quarter degree by quarter degree resolution. So that's how big each grid cell is. It extends from 50 degrees south to 50 degrees north. So you get quite a bit of coverage over the main populated areas of the Earth. This is also known as TRIM RT, or TRIM Real Time, and so this really is available every 3 hours. As soon as the satellite does all of its processing and it's transmitted down to Earth, then it's available for use in a hydrological model or a meteorological model or whatever kind of application you have for it. There are some alternatives to real-time data. If you're doing historical work, say you're calibrating a model on a river gauge over a decade-long period or over a 5-long period, that's all in the past. The rainfall has already happened, and so if you have some sort of archive of rainfall information, you have a good idea of what's already occurred at that exact location. So that's actually what this version of the TRIM product is used for. It's gauge corrected, and so in areas where the satellite instruments may not always have been producing perfect estimates of rainfall, if there were ground-based rain gauges that had other information or better opinions, so to speak, about what the atmosphere is actually doing in terms of precipitation, you can actually use this information to adjust the satellite rainfall estimates to get a better overall estimate of the rainfall. And so these are actually 3-hour estimates that are summed to monthly. The rain gauge data is accumulated on a 1 degree by 1 degree grid for that particular month. And then the various TRIM data products from just the satellite itself, those are bias adjusted and rescaled down to 3-hourly. So this is also known as TRIM V6 or TRIM V7. So when you hear TRIM RT, that refers to the satellite-only near real-time product. When you hear TRIM V7 and TRIM V6, that refers to a historical archived rainfall version that's been corrected by ground rain gauge measurements and is used mainly for historical or calibration type applications. So how do you get this data? It's great, it's out there, and it is available from multiple different sources, mainly from NASA's servers. So NASA is the US Space Agency, and they're the folks that actually launched and designed and operate the TRIM satellite, as well as all of the data feeds. So we have links to 3 separate FTP servers at the bottom of this slide, and you can visit any of those. You'll have to do some reading on exactly the documentation, on how all the data is organized and named and structured. But in any event, this stuff is available for people to use, for researchers, the general public, anyone who has an interest in this sort of work. Let's switch gears for just a moment or two and talk about potential evapotranspiration. The term forcing doesn't refer to just precipitation. The model also needs to know how much water is being lost to the atmosphere due to the twin processes of evaporation and transpiration. This is an important topic when it comes to droughts and water resource management. It's not so important for rainfall-driven flash flood events, primarily because rainfall-driven events tend to occur under cloudy skies, and so the sun is much less powerful, which means that potential evapotranspiration is much lower and much less of an impact overall on the water balance. So we prefer to use monthly averages of potential evapotranspiration just because the major factors that influence PET values, which again are primarily the sun, so the season, the sun angle, the length of the day, those things change on a month-to-month basis and less so on a day-to-day basis. They change every day, but those changes aren't that important to us, at least not for what we're doing here. That also has a twin benefit in the fact that it helps us reduce the data requirements for the hydro model. If we use mean monthly global PET, we only need 12 files total, one for each month for the entire world, and they apply to any year because, again, they're based primarily on the sun angle, and that doesn't change too much from year to year. And so that really reduces how much data we need to actually run the model successfully. So this global monthly mean PET, the version that's included with the training, it covers the entire world from pole to pole and from the international dateline all the way back around to the international dateline. The daily PET is calculated on a spatial basis using the Penn and Monteith equation, and then this data is standardized in accordance with research that's been done by the United Nations Food and Agriculture Organization. They've published a lot of research into this because this topic is exceptionally important for agricultural interests, farmers, and the like. The actual data is then produced by the U.S. Geological Survey and the U.S. Agency for International Development, or USGS and USAID. And so then once we have that daily data, that's averaged up to monthly data, and that's how the goods are eventually distributed out to the end users. If you're interested in obtaining the original daily data or in looking into more details about how exactly it's calculated or what equations are used, you're more than welcome to visit the website linked at the bottom. The PET data set is produced. Okay, so what we're going to do is we're going to transition into the hands-on portion of this module, and we're actually going to try to work with and visualize some precipitation and PET data. So I have my desktop here. I'm going to start off by going to my EF5 training folder. Again, the uncompressed version of this, not the zip file, but the folder itself. I'm going to go to EF5 training, and then I'm going to go into data and PET. And you see I have this test_pet.asc, that's an ASCII file or a text file. And then I have a zip file called bibimo, and that bibimo folder actually contains the PET data that we're going to be using. So the PET data is a grid, something that's a raster, and we know what we like to do with rasters. We like to open them up inside QGIS. So on my desktop, I'm going to open up QGIS Desktop 2.6.1. And once I'm inside it, I'm going to go to Layer, Add Layer, and I'm going to add a raster layer, Control-Shift-R. And this time, EF5 is, or excuse me, QGIS is opening me back to the old example2 DEM folder from the last module. So I'm going to get out of there, and I'm going to go to my EF5 training folder, data, PET, and then I'm going to open up testpet.ascii. And you'll notice that QGIS is giving me a little warning here at the top of my window. It says that the CRS, or the coordinate reference system, was undefined. But clearly that didn't matter too much because we can still see all of the Earth's surface. We can see all the comments and everything like we're supposed to. Now, what we're going to do is we're going to go ahead and add a second layer to this, another raster layer. And this time, instead of in the PET folder, we're going to go to EF5 training data and then trim, and we're going to add test_trim.ascii. So this is a test precipitation file. And I get the same thing, that CRS was undefined, but it's going to basically default to kind of a standard global projection that's used for this sort of data. So now you'll see over in the layers window, I have two rasters, test trim and test PET. Each one is going from black cells with the lowest value to white cells with the highest value. If I toggle back and forth between the two, when I look at test trim, I see just a black box with a lot of white stuff in it. It looks like it might be precipitation. And if I go the other way and I look at just the test potential evapotranspiration, I see all the continents and everything. So what I'm going to do is try to just change the colors to make sure everything is easier to see. So you can right-click on Test Trim, go to the Style tab, and then where it says Band Rendering, Render Type, you can do Single Band Pseudocolor and generate a new color map. And so for precipitation, I actually like something that goes from maybe white up to green. So I'm going to pick this one called Greens, and I'm going to say equal interval, and I'm going to pick just something like 15. And you can pick whatever you want, but this is more just so you can see what's going on. And when I turn that off, then you see now that I see a bunch of green on a kind of off-white background. And if I zoom in and look closer, sure enough, I see lots of areas that look sort of like precipitation. And I can use my Identify Features tool, selecting Trim, to go around and see what kind of values I get. And those values look pretty reasonable for rainfall in millimeters. If you want, you can do the same thing with the PET grids. I'm going to zoom back out to my entire domain. And when I right-click on Test PET, I can go to the Style tab and again pick pseudo color. And this time, I'm going to pick values that go from, say, purple to red. You can think of PET as representing sort of something related to heat, that the hotter it gets, the redder it gets, and red is a good hot color to use. And sure enough, that's what I see. And so this is actually the grid for January, which is summertime in the southern hemisphere and wintertime in the northern hemisphere. So the sun angle, and therefore the PET, is much stronger or much greater in the southern hemisphere. And sure enough, you see big bullseyes of high PET values in Australia, in southern and southwest Africa, in the southern half of South America, and you see almost non-existent test PET values in Canada, Russia, and northern Europe. And so this is kind of a good sanity check to tell us that we really are looking at something that looks like what we'd expect PET to be. So if you want to play around some more with the various colors on the files, you can go back to the properties of test trim. And one thing that's nice to do is if you're dealing with kind of the lowest level of the precipitation, basically where the precipitation is 0, you actually might not want to see that at all. And so we actually want to see if we can make that transparent where people won't be able to see it. And so whenever you actually right-click around these values, just a second. Or double-click, not right-click. And you can turn opacity from 100%. So opacity means that you can't see what's underneath it. If I change it to 0, then that'll make my lower level totally transparent. And now, when I turn the precipitation on over the PET, I just see the areas of precipitation, and the areas where it's 0, I can see the PET underneath. And so you can see rain kind of on the southern edges of the tropics, which is generally what you would expect during this time of year, when it's, again, southern hemisphere summer and the northern hemisphere winter. And again, really just go through this exercise, number one, to familiarize ourselves more so with QGIS, and also just to do a sanity check and make sure that we actually understand what's inside the precipitation file and what's inside the PET file. And I get a similar result on my screen now as what you probably see in the PowerPoint that goes along with this module. And one thing that's important to point out is these precipitation patterns, they do look like what you'd expect precipitation systems to look like. So that's a good sign. So what we're going to do now is get our precipitation and PET data ready for use in the Bogota River example. So I'm going to go ahead and exit QGIS for now. You can save your project if you want, but I don't need it, so I'm going to go ahead and close it. And I'm going to go back over to my EF5 training folder. I'm going to go to Data and then PET. And now I'm going to unzip Bibimo. So I'm going to right-click and go to Extract All. Again, recall that if you've got 7-zip or WinRAR or another compression utility on your system, you might have a slightly different command than I do. But in just general stock Windows, you have Extract All. And I'm going to click Browse. And I'm going to extract these files to EF5 training, examples, example 2, PET. So again, EF5 training, examples, example 2, PET. And I'm going to click Extract. And it took just a second, and now you see I have Bibimo, and then I have 12 files within this window that go from PET 0 to 5.01 onward to .02, .03, and each one of those represents a month: January, February, March, April, and on and on. Now let's go back and do the same thing for trim. So I'm going to go back to EF5 training, data, trim, and now I have trim 2002.zip. And I'm going to right-click on this, and again go to Extract All, and then Browse. This time, I'm going to go to EF5 Training Data, Trim, or excuse me, not EF5 Training Data, but EF5 Training Examples, Example 2, Precip. And you can see that's what I have in the text bar there. And I'm going to click Extract. And we have one precipitation file for every day. Or excuse me, we have a precipitation file every 3 hours for an entire year, and that's a total of 2,920 files. And so we're actually going to watch all of these go over into our new precipitation folder within example 2. And you can see as they go by the way that they're named, 3B42, and then there's RT. And remember that RT has to do with trim RT. These are trim real-time products. We haven't used the gauge-corrected version or anything like that because we're going to show you that even with the real-time products that just rely on satellite, we can still get really good results from the hydrological model. After you go past the RT part, there's a dot, and then it gets into the day and hour that the precipitation is valid. So you'll see that they're named in such a way that we go 2002 and then 08 or 09, so we're in August and then September, and then it goes through the days and then every 3 hours. And then each file name ends with 7r2.bin.gz, and so these files are in a zipped format, and that zipped format can actually be read natively by EF5, which is a really nice thing. So we're not actually going to have to do anything else with these files once this extraction process finishes. They'll already be ready to go and be ready to be read into the model. And whenever it finishes, you'll get a pop-up window with all the files named as we just saw. And you can also see down at the bottom of the window that it's telling you there's 2,920 items, and so if you go through and do the math and figure out how many files you have, that should be just about right for the entire year. Give or take a couple of days. So now what we're going to do is go ahead and exit that precip window. We're going to go back to EF5 training, examples, example 2, and we're going to open up the control.txt file, and we're going to check the precip forcing block and make sure that everything looks right. So the name of the block in this case is trim. That can be just kind of a generic name. We're using trim data, so why not? The type is important. We put trim RT because remember we're using trim real-time data. But if you were using the gauge-corrected data, you would put trim V7 instead. You can look at the README for a full list of other type of precipitation formats supported by EF5. The units are millimeters per hour. The frequency is that the files are available every 3 hours, so 3H. The location is in precip, so we can check that. We go to precip, and sure enough, there we see all of our 2,920 files. And then we can look at the name field of this particular block, and you can see that each file starts with 3B42RT dot. Then you have 4 digits to list the year, 2 digits for the month, 2 digits for the day, 2 digits for the hour, and then it ends with .7r2.bin.gz. So the file names match up with what we see in the control file, and that's what we want to happen. In the PET forcing block, we see some similar things. Here we have another generic name, FuseNet, because that's who provided the PET forcing to us. The type of file in this case is a BIF, or a binary file. So we're going to go into the location, which is PET/Bibimo. So I'm in PET, and then I go into Bibimo, and I see 12 files. And those 12 files are named as we would expect, PET025.mm, where mm represents a month, 01, 02, 03, 04. And these are available every month, so our frequency is M. Don't get month confused for minute. The frequency code for minute is U. So if you want to use month, you use M. If you want to use minute, you use U. And the units of this are in millimeters per hour. And EF5 is smart. It's going to read through each of these in order. It's going to basically change that mm into the number as necessary until it reads through all 12 files. So we have verified the names and the file paths match up with what we see in the control file. We'll go down to the gauge block, and we can see it's named Puente Portillo, which if you recall, that's what the name of our gauge is in reality. You could name the gauge whatever you want, as long as you change the name of it later on in the control file to reflect the new name. The longitude and the latitude need to be close. So you remember we used -74.6 and then 4.45, where we dropped that little pin or that little point in QGIS. So that's what appears here. We can check example 2 OBS, and we can see that Puente_Portillo.csv is in place where we'd expect it to be. And then we'll also put, for our basin area, 6,000. This is in square kilometers. And you remember we also told you in the last module that the basin area was about 6,000 square kilometers. We'll say that output time series or output TS equals true because we actually want to see the results from this particular model run. So we'll just leave that alone for now. In the basin block, you can see we've called the basin Bogota. That's also the name of the river. Again, the basin can be named whatever you want as long as you're consistent with that name later on in the control file. And then we're going to use the gauge name from the block above. So we're going to reuse gauge equals Puente Portillo, and we're telling EF5 that that gauge now is contained within this larger basin. And you may recall from the day one training modules that we mentioned that basin blocks are not physical basins. They're just a collection of gauges that you want EF5 to model together using the same sort of properties and tools. Multiple basin blocks also are possible. Each gauge must be at least in one basin, or each gauge must be in a basin block. You can't have a gauge out on its own, not in a basin block. And then there'll be something called a task block that we'll get to a little bit later. And in that task block, you'll actually give EF5 some of the commands for how exactly you're going to deal with that basin. My final comment on these gauge and basin blocks is that you don't need to use the actual names of the gauges or basins over which you're modeling. I find it easier to keep track of what I'm doing if I have different control files and I know what each one is named. But you could just as easily name gauge 1 and then have it be basin 1 and gauge 1 be inside basin 1. As long as your naming is consistent, you can name the gauges and basins whatever you want. You can name them apple and orange and banana, or dog and cat and horse. It doesn't really matter. You just have to make sure that you're consistent. And if you change the names and you make a mistake somewhere when you try to run EF5, it'll tell you what line the problem occurred on. It'll tell you if there was a problem with the basin name or a problem with the gauge name or a problem with the task block. That's one of the nice things about EF5 is that it is user-friendly enough to give you helpful error messages when things go wrong. So we'll give you just a few additional options for preset forcing and PET forcing. There are some other types available. For PET forcing, you can have just ordinary text ASCII files using Esri format with the header as shown on the slide. You can also do it with geotiff grids, and then we have the trim real-time and trim v7, kind of the built-in formats for satellite preset. If you're working in the United States or Canada and you're dealing with radar data, we can also natively read in what's called the MMS format, multi-rate or multi-sensor precipitation. In unit, you can use Y for year, M for month, D for day. All those things kind of make sense. Just remember that U means minute, M means month, and U means minute. You can also put in numbers before the time if you want. So you could have units of millimeters every 3 hours, or millimeters every 6 hours, or millimeters every 2 minutes, or whatever. It's pretty flexible in that sense. In the frequency, you have basically the same codes available to you, Y for year, M for month, and such. And in name, you also have various codes as well. You also have to be careful that you don't name your files starting with 4 Ys, and then you have a second set of 4 Ys that you want to refer to the year. Because when EF5 sees 4 Ys together in the file name, it's always going to think that's the year. So that's another thing just to keep in mind. Similar things are true for the PET forcing. It can also read in ASCII files or binary files, which is what we're using in this example, or geotiff grids. Any of the three are acceptable. And then the unit, frequency, and name lines all operate identically to how they work in precip. If there are any additional options that you're curious about when it comes to precipitation or PET forcing, you can always consult the EF5 README, which contains an exhaustive list of all of the different options and commands that can be used within the control file. In the gauge block, there's a few other options to mention. Rather than using longitude and latitude, if you prefer to be marking where your gauge location is in grid cell space, if you say you want to know that it's 50 grid cells to the left and 40 grid cells to the north, you can use that instead of the equivalent latitude and longitude. The only difference is if you use that, you need to change lon and lat to cell X and cell Y. Basin area is actually optional, but we do recommend it. We're going to use it in this example. EF5 basically uses that value as where it's kind of looking in the flow accumulation grid to find the closest match for where the gauge location is. So if your flow accumulation grid is all good and you don't have anything weird going on around the edge of it, you should be fine not use that option, but we generally like to use it just to be safe. If you do output time series or output TS equals true, that means that we'll actually get the output written to file. And then if you do want DA and want CO, those tell EF5 to do data assimilation with the gauge or to include the time series in what's called a combined output file. Those are fairly advanced options. We aren't going to get to use either of those with this training, but you can consult the EF5 README for more information. So the bottom line in all of this is that EF5 will tell you if there is a problem with the control file. If you have a file that's missing or a file path that's incorrect or part of the task block doesn't match up because you changed a name in one place and forgot to in another, don't panic. You'll run it, you'll get an error, but it'll tell you where the problem is. It's not the end of the world. You can open up your control file and try to fix it. But Kind of the bottom line with all of this is just that control file errors are there to help you. They're pretty much inevitable. We've encountered many dozen control file errors in producing the training. It takes a while to master this stuff and to become familiar with all the options and where everything is. And those errors, they're there actually to help you. So when you get one, just don't panic, and you should be able to figure it out without too much problem at all. So that concludes Module 2.1, Rainfall and PET. The next module that will be filmed is Automatic Calibration. That'll be Module 2.2. Until we get to that point, though, if you're interested in learning more about rainfall and PET, there are multiple references available with the training package, including a paper on how evapotranspiration is calculated. There's also the paper that describes how the trim precip products are produced. And then you can also look into the Handbook of Hydrology, which is not available with the training, but is available from other sources. And check out the Handbook of Hydrology for additional information on the equations for exactly how PET is calculated. There's also a training document about EF5 control file that contains a bunch of additional information on how the different control file options work together and interact with one another. And then, of course, there's always the EF5 README that would be recommended reading as well. So thanks very much for joining us, and we'll see you next time.